Now the most important point which I want to get to here is the CDF and PDF of continuous random variables. Earlier we had defined the CDF and PDF as ways in which to you of assigning a probability measure to an experiment where whose sample space was a portion of the real line, right. But they are more commonly encountered as properties of random variables, and so we have to make the connection between what we said in the previous lectures and our definition right now of continuous random variables. That just remember that continuous random variable means omega x is uncountable, that is all, right. So we really do not know at this point what kind of probability measure this continuous random variable is going to inherit. In fact, we cannot say beforehand, because we have not talked about the probability at all. We have only up to now only defined how to assign values to of the random variable, right. So we have to now bring the idea of probability, right, and of course we, right, for that we need the CDF and the PDF, which is I mean in the case of omega equal to. So let us start with the simplest example. Consider the sample space omega as some subset of R, which is again the same thing as here, which is but I am not necessarily going to restrict myself to spinning point. It could be any experiment where omega is some subset of R, right, and then of course I have the script f being the Borel sigma field on for that particular subset of, or you can take it to be all set of all intervals, it does not matter, right, whether R or sigma, it does not matter anyway. So then you have the probability measure P for intervals. This is what we spent a lot of time doing, right, in a couple of lectures back. So now we have the probability measure on this defined on intervals of capital omega, and let us say P is specified using either a CDF or a PDF, does not matter. In other words, we have our entire complement of omega f and p, right, which is the basic probability experiment that is central to any construction of probability. Okay. So we have omega fp, and I am not again specifying which CDF or PDF to use. As we can see, we can use many different types of PDF, CDF or PDF models, and all of them will be consistent, and therefore at this point we are saying that we are letting things be as general as possible, right. Okay. So now bringing the random variable. So let us look at the simplest case of x of omega equal to omega. So together with this capital omega and this x, we have defined, right, the random variable x such that which is exactly what I wrote out here, right, and now we want to now look attach this CDF, okay. Now I need to bring in the notation here for CDF. So CDF we will denote in general with the script capital F and the PDF with a small f. So these are functions, that's why I am not putting the name of an argument here. So the CDF is denoted by this capital F. So what is the CDF, right? So basically, as we pointed out earlier, the interval minus infinity, so the CDF by earlier definition the probability or the value of the CDF at any for any real argument is basically the probability of this interval. right, going up to and including the value of the number that we pick. So, if we pick some, okay, to make it even clearer, let me write some x naught here if you think that will make it, if it will be of some help. Like we can picture the CDF defined at the right at the value at the number x naught to be the probability that we are assigning to this interval, right, which is the set of all real numbers smaller than or no bigger than x naught. Okay. So, now this is the definition of the CDF regardless of before we even brought in this random variable. Now, we bring in this random variable and it is clear that this interval, now this interval minus infinity to x naught is basically identical to this, to the event that, or let me not write put equals here, is the same as, or is identical to, is the same as the event that the random variable takes values no bigger than, no larger than x naught, because of this way of defining the random variable, right. So, you get some number between minus infinity and x naught, that is the value taken by the random variable, and therefore the random variable has to be no bigger than x naught. So, if you define this for any experiment where the sample space is some portion of the real number x, you define x of omega equal to omega, then this is identical to this, or the same, these two are the same events for all values of x naught. Any real number x naught you pick, then these two have to be the same, and therefore the probability of this event is the same as the, now, right, you can go from the you can attach the random variable to the CDF, right. So, therefore, so the f becomes the CDF of x, the f becomes f with a subscript x. So, here of course I have given primacy to the CDF because the CDF is as I will discuss in a couple of minutes from now, is a more mathematical general way of assigning probabilities than the PDF, but still, right. So, this may sound like a kind of a simplistic argument, but it's really not. I mean, it's because this, if you right, this it is based on this fundamental idea or this basic idea that you understand how an arbitrarily defined CDF like this could be attached to a random variable, and therefore once you attach the CDF you can differentiate it, and the density function will follow automatically, assuming that, right, when your CDF is differentiable, or I mean this, and we have said that continuous functions also quote unquote can be differentiated. So, we will, so if f is even right, if capital Fx is continuous, then small fx of x, that is a CDF, a PDF of x becomes the right, we are going to right, in the sense that here we are not going to worry about the differentiability angle so much, as we already said in some previous lecture. Continuity, I mean continuous is and reasonably smooth in the sense that the number of kinks in capital F is going to be are going to be very small, right. So, therefore, the problematic points in the differentiability of small capital F are not going to matter, and basically more or less continuity of F will be enough to ensure the differentiability of F in most engineering cases, right. So, we do not strictly we should include, right, any continuous case, even though it may not be strictly differentiable in the mathematical sense. So, at the points where you cannot assign a unique derivative, as we said earlier, you can assign a consistently, you can take either the left derivative or the right derivative, it does not really matter. Okay. So, this is a simple case of this x of omega equal to omega. What do we do in a more, right, in a more complicated case? In general, right, how to this is what we should look at. How do we calculate or specify the CDF of a continuous random variable x? Why do I notice that I am saying CDF? Because as I said, conceptually the CDF is more important than the PDF, although computationally it is the reverse. The PDF is more important than the CDF. Right. So, how do you define in the general case the CDF of a continuous random variable? Right. Basically you do it using the definition of a CDF. This f, the CDF of x, right, which is written by denoted by capital S subscript x at any, right, for any real argument x naught being any real argument, right, is basically defined to be the probability of this event x, that is it is defined to be the probability that x takes a value no bigger than x naught. So, this basically is nothing but the probability of the set of all points of omega now, right, because I am talking about general. So, all points in omega, that is general omega, such that what x of omega, capital X of small omega, that is a measurement there is a mapping or a measurement on small omega is no bigger than x naught. So, this probability is not in general an easy thing to calculate. It only becomes an easy thing to calculate in some very simple cases like this. In general, if you look at some complicated space and you define a complicated function capital X, this is not an easy calculation to do in practice, and therefore we cannot talk about a general calculation of this kind, because we do not even know how to assign probabilities, for example, to arbitrary sets of to arbitrary omegas in r power k or whatever. But anyway, we have to only take one thing at a time, right. So, we will make the definition and then apply it as we go along. That is the simplest thing, that is the only thing we can really do, right. We can say, okay, we will keep this as an operational definition of the CDF and of this x, right. So, essentially we are saying that the CDF of the random variable x, right, at any for any x naught, any real number x naught is the set of all points in, right, in the space such that the measurement capital X now is basically a measurement on the sample point omega, a real measurement on the sample point omega is no bigger than the number we have selected, which is namely this x naught. So, if we are going to do this, let me write it here for all x naught which is, right, for all real numbers x naught. In other words, this capital F, as we said earlier, is basically, right, is a mapping from the entire real line to the interval 0 1, because it always takes values only between 0 and 1, being a probability. We have said this several times earlier, but anyways, now the only thing we are doing is we are attaching this subscript to the F. So, this is, right, this is a general procedure for doing this. And now let us let us take the case of let us take the case of the spinning pointer. Go back to the spinning pointer example and see how we can mathematically go through this, where it is easy enough to do, right. So, we do not have to break our head on how to calculate this probability. In general, I have to warn you that this is not an easy calculation to do in general, but right, only in some simple cases it is easy. So, we will pick an easy example and do this calculation and then try to talk about it a little bit, but there is not much more we can say at this point, because this becomes highly specific to the particular experiment under consideration.